University of Science and Technology. Today, the fourth lecture on this series will be handled by Dr. B. Kannan from IMD. So, good evening to all as per Indian Standard Time. So, before beginning, I invite Professor Dr. Someshwar Das sir, Secretary SAMA, to propose the welcome address.
Okay, thank you very much, Dr. Avilas. Am I audible?
Yes, sir.
Yes, sir.
Okay. I'm so sorry that I'm late today by 10 minutes because my Zoom link was not working. So anyway, sorry for that. AVM Dr. Ajit Tyagi, President of SAMA. Today's speaker, Dr. B.A.M. Kannan, scientist in India Meteorological Department, members of the organizing committee, participants from, I think, almost 46 countries. Ladies and gentlemen, I welcome you on behalf of South Asian Meteorological Association and Advanced Center for Atmospheric Radar Research, Cochin University of Science and Technology. Okay, this is the fourth lecture of the lecture series on radar meteorology. You know, it is a continuation of our efforts on capacity building for the people of South Asia and the member countries of non-aligned movement. Most of you already know that this is our fourth attempt on the capacity building. I'm just trying to repeat it once again because the speaker is new today, and also some new participants registered during the last 1 week. So this is the fourth attempt on capacity building. Our first attempt was on atmospheric physics, in which we delivered, organized 16 lectures. Then was on the WRF modeling system, in which lectures and hands-on trainings were given in coordination with the CDAC, that is Center for Development of Advanced Computing. The third lecture series was for 20 weeks on satellite meteorology, and this is the fourth lecture of the fourth lecture series. In this lecture series, as on yesterday, I think about 1,175 candidates have registered for this course. They said from about 46 plus countries. As per the rule which we had mentioned earlier during the previous lectures, that we shall give at the end of the lecture series certificates to all those candidates who secure about 75% of attendance or more. And also at the end of the lecture series, we shall conduct an evaluation test in which further grade certificates will be given to all those candidates who will score above 85%, above 80%, and so on. And accordingly, we shall grade the certificate as outstanding, excellent, very good, and so on. So this is a very important lecture series in which we have received many good feedbacks from the participants. I'm sure that you all will be benefiting with this lecture series. Many of you who are not able to attend the lecture series on live because of the time difference in different countries, for all those, these lectures will be also available on the YouTube channel of SAMA even after the lectures are over. So those who could not attend live, they can always attend on the YouTube, watch on the YouTube. So please write your questions at the in the question answer chat box, and it will be taken up by the moderators and answered by the speaker at the end of his lecture. So please enjoy the lectures and have a good day. Thank you very much. Over to you, Dr. Avilas.
Thank you, sir. Thank you very much, sir. Now I request Professor AVM Aditya sir, the President of SAMA, for proposing the formal presidential address.
Thank you, Abhilash. And am I audible?
Yes, sir. Yes.
Thank you. Dr. Pradhan, Chairman of the Organizing Committee of Radar Meteorology, Dr. Kawun U from Myanmar, Dr. Shah Alam, Dr. Professor Someshwar Das, members of the Organizing Committee. I join Professor Someshwar Das in welcoming all our distinguished panelists and speaker, Dr. Kannan, and also the participants. As mentioned, it is the fourth lecture, and some of you may have joined this as the first lecture. So I request you, as Professor Somesh has mentioned, please go through the lectures which are available, because it is essential for you to have a background knowledge of these. And all those three lectures were I think, covered very well. The inaugural lecture by Professor Chandrasekhar, which talked about the infrastructure, use of radar as an infrastructure at the national, local level, and also Professor Mohan Kumar, who talked about the atmospheric radars, which is useful for tropospheric and stratospheric studies, followed by two lectures, basic lectures by Dr. Pradhan, who covered, I think, the basic concepts very well with examples, and we had a very, very good question answer session. And the fourth lecture is by Dr. Kannan, whom I had known from 2008 as a young man. Now he looks like a senior professor. And what I've seen him is that he moved to Delhi during the winter season, and he used to be smiling in the plain shirt only. Very, 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 I think, sincere, dedicated. And over a period of time, he has proven himself as a good operational meteorologist, as well as a researcher, also using the radar for the applications. So great. And thank you, Kannan, for he agreed to deliver this lecture. And I'm sure you will be covering from what Dr. Pradhan has covered already, from there on to the Doppler aspects of the radar and radar relationship and various unique features of the radar and their application and products. So over to you. You will have a good number of questions, so be ready for that also. And I request all participants to pay attention, make full use of this important lecture, because dual radar is the thing. All our subsequent lectures will be built on the applications of the radar and all that. So the basics of the radar, the dual pole characteristics, should be understood, and this lecture will help you to develop that expertise. So once again, thank you, Kannan. And let me also compliment Dr. Pradhan and organizing committee for planning this lecture series so well planned systematically, and have also ensured that we have the experts in the country to deliver these talks to the participants. Thank you. Have a good session.
Thank you. Thank you, sir. With the permission of the chairman of the radar committee, Dr. Pradhan sir, we'll be starting the lecture. Before starting the lecture by Dr. Kannan, I request PP Srikala from Department of Atmospheric Sciences, CUSAT, to introduce the speaker to the audience.
Extremely glad to introduce Dr. V. Arunmalar Kannan, who is serving in Indian Meteorological Department as Spanish F. He has developed his passion in weather radar technology during his initial career at the first indigenous Doppler radar. He mastered radar technology and applications through hands-on experience from the endeavors at the prestigious institution. He adopted special scan strategies for
Mic is on. Mic is on. Is it audible?
Yes, sir.
Okay.
Okay. Not so clear although, but it's okay.
Yeah, please continue.
He adopted special scan strategies towards nowcasting on launch-related activities. He also successfully demonstrated it during 2010 Delhi Commonwealth Games. He was a significant contributor to radar networking and the conceptualization of central server. The server enabled the unification and the customization of products for a heterogeneous framework, allowing user requirement-based data formats to be gathered in near real time. He leads the radar application group at IMD, promoting in-house core radar research and the implementation of effective operational nowcasting products. He also shares this acquired knowledge through WMO ITC, WMO SK2 training, and the IMD in-house training program. He currently manages the country's first Doppler Weather Radar, installed over 23 years ago in Chennai, ensuring its upkeep and generation of data to the highest standards. He is currently serving as co-PA on NARM projects with Amity University, Noida, IIT Bombay, and IIT Bhubaneswar, and is engaged in research collaboration with IIT Guwahati, IITM Pune, Andhra University, Chennai, IIT Chennai, and various other institutions in and around. Additionally, he provides radar technological support to the government institutions such as IITM and the state disaster management agencies of Tamil Nadu, Uttarakhand, and Uttar. We are incredibly fortunate to have Dr. B.A. Kannan with us today to share his invaluable insights and knowledge on the basis of Doppler Weather Radars.
Kannan sir, please.
Very good afternoon to all. Thank you so much for giving the opportunity. My sincere gratitude to the President of SAMA, Dr. Tyagi sir. I am very privileged to work under him. And of course, Somasat Das also, we were in various committees, especially in making the FDP program. He played a pivotal role. And most of the panelists who are there, we got associated in the process of my learning. And I sincerely thank in giving opportunity for me in presenting, in having a discussion on those topics. And of course, Somasat Das also, we were in. I think, sir, my screen I could not share.
Is everything okay?
Sir, your co-host, I think you can share it.
Oh, yes. Yeah, now I got it.
Yeah.
As most of the panelists were saying, literally we are slowly entering into the mainstream. Today again, it is going to be slightly on the fundamental side, starting up with the nature of the Doppler Weather Radar, and we are restricting our discussion only with the single polarized Doppler Weather Radar. Subsequently, much of the products also, when it goes there, will be progressing into the dual polarized. Of course, some few slides I kept it for a continuity in creating interest. Today, the topic has been divided into 4 subcategories that each I will take some 10 minutes. In between, whenever there is a question also, it can be answered parallelly. The first discussion is on Doppler effect in electromagnetic waves, the unambiguous range, velocity, and dilemma. And subsequently, we will be progressing into Doppler weather radars with different bands of operation, which is normally used and what we have it in IMD. Then finally, we will be going up with the 3 base products which can be derived from Doppler weather radar, and out of which the most primary one, the radar reflectivity, how we are going to take it and calculate the precipitation or the derived rain related parameters from that. With that, we will be concluding the today's discussion. So I'll proceed with discussion 1, where it says about the Doppler effect. Doppler effect, literally the classical way it was proposed for sound. As we all know that when an observer or the source is having a relative motion, there is a perceived change in the frequency, which was discovered very well long ahead before 1842. And subsequently, not only Doppler, there were 3 different scientists who co-invented a similar scenario, including Liuzhou. And the process of this could be very easily understood in sound. Basically, as this all human beings, we can hear to it. And the sound of the velocity of the sound also is quite minimal, somewhere around 300 meters per second. We could apparently see, and you can see here what the diagrams which has been shown. I borrowed it from the web, where a vehicle is moving towards a stationary observer, and in one of the direction where the vehicle moves around towards the observer, he is feeling about a change or the increase in the frequency, and on the other direction he is going to have it less because of the wavelength changes, as wavelength and frequency are interdependent. And this is literally, if you see to the right, we have the formula. What the formula is perceived by the observer is F, and what is going to be that is based to the ratio of the velocities is totally asymmetric. As the observer moving or the source moving is going to change the pitch, but it is not at the equal scale, as it is going to be having a division factor rather than a linear addition or of that sort. So saying in this, now this effect, how we can apply it to sound. So when we come on to that, we'll be feeling the biggest difficulty or whatever the conceptualization in physics is going to be. As velocity of the sound in vacuum is going to be a constant, and it is not going to change with any observer on a related platform. In the case of sound, if the person sitting in the car and the person standing on the street, both are in 2 different relative frames, and ultimately the frequency change can be different. But now in the case of sound, how we have to go up with? As finally, when we said the relative velocity is not going to be there, it is a universal constant. So what happened was that you can see superficially that if a person, you imagine that a person travels at the speed of sound by holding a mirror in his front, and we know that whatever we see in the mirror is nothing but the reflection of the photons, which again is going to travel with the velocity of sound. Now the person himself, when he is traveling at the velocity of the sound, whether he can see his face in the mirror. So this superficial questions and other things was discussed in elaborate. And finally, the special relativity theory was brought into the picture, where the velocity, rather than adding up with the sound and other thing, we will be using it as a ratio, as we did it with Lizau's equations. And Lorentz calculation subsequently followed, which demands that it is the ratio of the speed of the observer to the sound which is to be taken into effect, rather than a direct addition or subtraction. That's why if you see to the right, you have this equation, v plus u prime divided by 1 plus uv divided by c square. V is going to be the velocity of the signal which is going to be passed upon, and this is u is going to be the person on the relative frame. Now, when you substitute c on both the things, you will be finding finally that it is going to be again the same c. But when you go in the frequency calculations, you can see that because of the time dilation, length contraction, which most of us we studied in our earlier career, same thing is applicable. And finally, the observed frequency emanating out of a source Fs is going to be this minimal change within the square root of 1 minus u by v by 1 plus u by v. And if you see, the velocity of sound is going to be almost 3 into 10 power 8 to be more appropriate, 299792458 meters per second, or literally it is 300 million kilometers per second it is going to travel. And the fastest speed which normally the human beings which we are going to be only is in the term of 2 or 3 Mach numbers. So the speed is not going to be heavy, and ultimately the frequency change is going to be very minimal. Having said to the theory, we will be going in detail. Now the frequency cannot be measured. Then whether there ends the tale, whether we can go ahead by measuring the velocities. So when this curiosity comes in, when you consider a wave, any wave has 3 properties. One is going to be its amplitude or a representation of its power. And second thing is going to be the variation in the time sequence. The third is going to be the phase. The starting phase, if it is a very highly stable system, the phase change also can matter to show up a difference in the frequency on small fractions too. So that way, we are trying to attempt that whether by measuring the phase, we can measure the shift. Now for that, a diagram has been kept where the radar, but of course here the radar representation is shown. I borrowed it from the web. It is for a tracking radar. The weather radar also is quite similar as it is going to emanate the signal. Now instead of a target which is going to be aircraft, here it is going to be cloud. So you imagine that there is a target separated by a distance r from the radar. Now the signal which goes through and comes back, because of the shift of the target, there is a very slight change in the phase. Now we are trying to attempt whether this phase change can be measured. Further, the equation which has been kept is, that's why if you see earlier days, most of the Doppler radars wanted a very high stable system and we went for klystron based systems. Of course, with the later developments in the processing technique where a bus pulse can be used, now magnetron systems and other systems also are capable to be used in determining Doppler. Otherwise, analog radars, most of the thing as you see, it will be using magnetrons. Even in IMD, if you see whatever the radars we have now is going to be a very highly stable system, as all the radars which is operational in the country is of Doppler nature. Either we use a klystron or with the recent solid state power amplifiers. Being amplifier, literally it is the master oscillator which is going to generate the frequency and it is going to be very highly stable. There is no much phase change. The phase change is going to be very minimal except for the thermal noise. So that way we are going for a very high stable phase. This 50 is the initial phase of my signal. So when this initial phase is there, now I am trying to calculate the distance in terms of phase. So how to do? You remember I got a distance r. While going it was r, while coming back again it is r. So it is totally 2r. I am trying to sample it in wavelengths. So how many completed wavelengths is going to be? Then the remaining fraction of the wavelength I am going to convert into a phase angle. So we got this equation with minus 2r by lambda. 2r, as you all know, this is going to be a monostatic radar. That means the same antenna is going to receive back the signal. So your receiver also is located at the same radar site. So your distance is going to be from the target, from the radar to the target and again back to the radar. So each distance we take it as 2r. So 2r divided by lambda is going to be there. And as you see that a complete wavelength lambda corresponds to a complete circle as a simple harmonic motion. So we add a multiplication factor of 2π. Now what I did, I transmitted a pulse. Now I got a return pulse after interacting with the target with a small phase change. I wanted to know how much phase change happened. So what we did was that we taken the differential of that to see that between the two pulses. So when you calculate it 50 as it is a highly stable system, it is not ingesting any phase variations. Now whatever the variation came is only because of the target, and you know dr by dt is nothing but the velocity. The rate of change of distance is going to be velocity. So that way you can find velocity, and d phi by dt is nothing but your angular velocity. Angular velocity can be referred in terms of frequency as 2π nu, and now this frequency is nothing but your shifted Doppler FD. So I had a shifted Doppler frequency which could be measured by knowing the velocity and this variation of the angle. So 2π and this came up. Now I am going to reverse calculate it. Now FD how to find? Now FD again, what we are going to do is, as we are going to use a pulse radar system, we are trying to calculate this in terms of the pulse repetitive frequency. So what we do when we are dropping pulses, how many pulses you are trying to push out in a second, we say it as the pulse repetitive frequency, and the time between the pulses we say it as pulse repetitive time. Now the Nyquist theorem, what it does, now this FD to resolve it, what I have to do, I have to sample it almost twice to that of the frequency. That's what the demand is going to be minimal. The Nyquist theorem demands that at least twice you should have your sampler frequency more. So ultimately attributing for that, the formula has been changed. Instead of V, I put it as VU, as U is going to be the unambiguous velocity, which is going to be there. And lambda is going to be my operational wavelength, which was in the denominator went out, and instead of FD, I put it as PR by 4. So now, having the frequency, I know how much the maximum frequency can be measured. So this is the way we are trying to do. And here we have some 3 different bands which we'll be discussing subsequently, which commonly is used. There is a S-band system. All this nomenclature has been kept only to create confusion that people should not understand. As you know, Pradhan sir also might have discussed, as radar was mainly developed for defense purpose, they wanted that the other person should not know the operational frequency, otherwise jamming and other things may happen. So ultimately this S, C, X, K, Q, what else, V, W, everything was brought into that to avoid the other person not in knowing. But of course, now when the technology opened up, we started adopting the same jargons, as we could not come up from our mathematics with theta, phi and other thing. These jargons we radar meteorologists didn't change, and ultimately it became like a fashion. Even now we are trying to continue. So that's how these band names, other thing has been kept. And the PRF, there is a restriction because of my engineering design. I can go up to 240 to 1200, and ultimately the velocity which can be sensed also has been shown. So if I have a S-band radar, I can measure to a maximum of 30 meters per second. And if I have a C-band radar, the maximum I can measure of 15 meters per second. And if I have a X-band system, I can go only up to 6 or 7 meters per second. This by the theory. Initially, what we discussed was that the Doppler effect in sound, then how it varies with velocity of the light when it comes into the picture. And as you cannot change it, that directly measuring of the frequency of a very small quantity, as it became difficult, we were trying to measure it in the terms of phases. That normally most of the people who are already in the radar, they'll be knowing about the IQ modulation. We divide it into 2 channels, and from there we try to derive the power and the phase. That anyway, as a base product, we'll be discussing that back again. So that way, finally we get those values, and from there we are trying to see whether we can measure a velocity. If at all, and a velocity be measured, what will be the maximum limit? So till that we discussed as of now. We got all those values also for some 3 different wavelength bands with the operational frequency or the PR of which we kept it for that has been shown. Now, having said, I thought I'll keep one more slide as a remembrance, as already Pradhan sir might have discussed on the last week, as some of the parameters of the radar was discussed. One was the pulse repetitive frequency. And I told that there is a limitation, PRF and PRT are one over the other thing. Pulse repetitive time or pulse repetitive frequency is nothing but one over the other. So that way it is there. Now my pulse width divided by pulse repetitive time is going to say about the duty cycle of the system. If you are using a klystron or any of the vacuum tube, the duty cycle is going to be very, very less of the order of 0.01%. So to that extent only you can operate. You cannot continuously keep it radiating upon. So that is the limitation. We have to restrict our PRS. And in this process, now someone can say, okay, anyway, for my duty cycle to meet the PRT, yes, there is a restriction. Why can't I change the pulse width? Now changing the pulse width is going to determine about your minimum discernible signal. So I wanted the pulse width also to be slightly higher. Then pulse repetitive time also to the higher side. Finally, my electronics, how much is going to be my restricting time is the only one which is going to create a restriction. It's not only stopping with the minimum discernible signal, including your occupied bandwidth, which goes for the licensing. That also has a say. When I go for a very narrow pulse width, then the frequency domain, it's going to be broadened out, as you see right over here in this below. And you have one over that in the top also. I'll take a laser pointer. So you can see this is for the smaller pulse width. And when you go for a higher pulse width, the occupied bandwidth goes lesser. And these are some of the radars where we have it. Now, because of the pulse width and other combination, you cannot detect to minimum value, which is described by MDS. So when it goes with the range, it also goes increasing. So weaker echoes at further range detection is one of the trickiest job even today. So having said, I'll again progress into range. Now we found, yes, velocity could be found. Now how about the range? As radar, the nomenclature itself, what it stated is radio detection and ranging. So I want to find the range. Now I have a PR pulse, I am sending it in a sequence. So once I drop the stone, you imagine I made a stopwatch on, or I kept my receiver on, and I go on sampling between the next pulse time. So up to this, whatever I will be getting a back return, I can go on sampling. I will be putting up that as a representation. So that way, only this much time, that interpulse period which is shown, of course, this pulse width we have to subtract it. During that time, my circulator is not going to permit the high signal to come and damage my receiver. So the effective time is going to be only this much. That now again, this factor of 2, you know, 2RU. 2RU is going to be, R is going to be the range. 2 times R is going to be time into velocity. Here the signal travels with the velocity of light. So C and the PRT. So now my unambiguous range is determined. Again, PRT we said it is one. It is almost the reciprocation of PRF. So it is C by 2 PRF. So this is on the range. So one factor we found for the velocity, and the second factor we found for the range. And the unfortunate part is, in velocity, when we found, it was for the PRF was on the numerator. What we calculated was, it was lambda PRF divided by 4 was there. You can see here, lambda divided by 4 was there. So when your PRF increases, then my unambiguous velocity will increase, but at the cost of my range. You can see the PRF in the denominator, and ultimately it gives a restriction on a proper resolved range. What you can see is this, for an easy concentration of the people who are not exposed to the radar meteorology. Some of you may be good in photography. What you do is that when there is a fast moving object, what do? I try to reduce my aperture time, or what I'll be doing is immediately I should open and close my shutter. So that way, PRF is nothing but a happening of the change between. So I should send pulses very frequently. Then only I can properly diagnose the velocity. Similar thing, that's how there in the equation, you can logically conclude that the velocity is going to be proportional with the PRF. But when you want to see the range, like I drop a stone, I put a stopwatch and try to measure the back returns, I have to wait till it encounters the target. You imagine I dropped a stone, and the second stone was dropped. I could not get the return from any of the stone. Now my stopwatch is resetted with the present pulse. So what happens is, in this process, I got back a return. I am not sure whether it came from the recent pulse or from the earlier pulse. Most probably, logically, you know, it could be from the earlier pulse. This creates a unambiguity. So I have to reduce my pulse dropping to see very far. That way you can see to it, PRF is in the lower, which logically concludes to our observation. Now, having said, we again started for all the same calculations. So if I have a S-band system, you can see it is not going to have any say on the wavelength. Either S-band or C-band or X-band, it is going to be dependent only on your operational PRF, nothing more. As velocity of light, you know, it's going to be a constant. So it is not to restrict the range. So range, you can see now only the earth curvature and your transmitted power is going to say that how far you can see with your radar, and your unambiguous range is going to be determined by your PRF. But now we came into a dilemma. That's what we say it as Doppler dilemma. So what is Doppler dilemma? Now the problem is, I had an unambiguous range. Unambiguous range depends inversely to the PRF. And I have an unambiguous velocity, which is directly proportional to the PRF. When I take a product of both the things, it is a constant. So which indirectly means that if I am more focused upon getting a very long range return, then I cannot sense the velocity. Now, if I am very much focused on seeing that what moves faster and other things, now I cannot see for a very long range. So this creates a dilemma. So that's how Doppler dilemma has been kept. That means you are into a dilemma to decide whether your measurement in velocity is of more importance or on the range. So now I kept some images, which was my learning in the very first radar. That time we had the liberty in changing the PRFs and all the combinations. Here I put it that range folding is there, no? You can see some wedge-shaped echoes which are represented, which came because of a farther return. It got folded and it was represented at a false position. And if you see in the actual, it is removed off. You can see many wedges are there. Here one, here. Almost this entire region is filled with the second trip returns. So normally, a radar meteorologist can easily identify. But our new person has to do. Only thing is that when you are sending a beam, you are sending a narrow pencil beam. It goes on expanding with the range. So once you do that way, when you are getting a return at a farther range, what you sampled was a very big echo. And when I tried to represent, it came on a very small range. So that way I'll be getting a wedge type of structure closer to the radar and protruding out. And the reflectivity values will be normally less. Why? You got the return somewhere very far off where your MDS was so much lesser. Only thing I brought it closer. Again, my multiplicating factor of R square is very less. So I'll be getting the echoes much weaker than at the surrounding echo region. So that is one easier way. Even if you get an echo of this sort, you can easily identify that there is a second ray. So what we radar meteorologists try to do is how to come out of the dilemma. So there are some procedures. We adopt the procedure to get it unfolded like this, what we are seeing it over here. There are at least 2-3 techniques for range unfolding. Similarly for velocity unfolding. So logically you people might have known. Now my problem of folding came only because I could not distinguish one pulse to the next pulse, right? As my stopwatch was set with the recent pulse. You imagine I given some color coding. One went with the red color and the second went with green. So now when I got the trace written with the red signature, I am sure it is not from the recent pulse, it came from the very earlier pulse. So that way you can phase code your signals and try to retrieve back. Now you are sure whether it came from the recent or from the previous or one previous. If you have a good computational power, you can go for multiple range unfolding. Similar thing is applicable for velocity folding, which we'll be discussing. So if nothing is there, only with the earlier equation we go up with, you can find for different wavelength bands. If you want the unambiguous range to be increased, automatically your sensible velocity from the top, it goes on getting reduced down. So at 250 kilometers, even in our calculations also, we could find that we are getting somewhere around 30 meters per second for a S-band radar. Then half of that for a 5 centimeter radar and still half of that for a X-band radar. So now XCS has been kept in some numbers. It is the operational frequency measured in terms of wavelength. So I put 10.6, normally 10 centimeter we take as a paradigm for S-band radar, 5 for a C-band radar and 3 for a X-band radar. So you can find if I use 3 different wavelengths, it's having its own difficulties. S-band stands out. You can find the velocity as well as the range to a better resolved one. So this is one advantage of having S-band radar. Now this velocity also you can see, no? What I say folding is, suddenly there will be a color change like all these colors coming and going with the entire spectrum of your plotting colors. Normally the velocity is coded as to the frequency redshift. The outgoing colors are going to be warm and the incoming colors are going to be cool colors, especially on the blue range. So you get a mix of coming and outgoing, which is going to be totally a noisy data because of multiple folding happening in the phases. So you got all those things and this is the way to resolve it. Now you can find all this way it is going to be cool blue colors. So these are going to come to you. Cool blue represents even a negative velocity, right? As it is an increase in the frequency, which is going to create that. So the frequency and that lambda we are trying to use it, that way it is going to be changing, having a negative effect. That way you get the colors reversed. So minus velocities are incoming, or blue color incoming and red outgoing. So here I can find the wind comes from this direction, somewhere on the southeasterly, and which is coming into the inland. So these are the things you can find only with this. Now you could understand Doppler dilemma. It is just to represent your unambiguous range and unambiguous velocity, whether it's having a problem. Now, how to solve it? As already it was told, now one process other than color coding, what you can do is, I sample with two different frequencies. So in one case, I got a return in some portion, and in the second case, I got the return represented in some other portion. That means both has a difference, which may not be right. As your target and your source is going to be on the same location, if there is a difference between both, you can presume that the returns are not belonging to the right position. You can remove it off. Or if you know the methodology to remove, put it back in the original position, you can remove and put it on a distance location. So that way, this is the very easiest technique which you can adopt in a Doppler radar to improve both your unambiguous range as well as the velocity. So this scheme, we say it as dual PRF, but normally in the operational sequence, we go for a staggered PRF. That means each pulse, when it is changing, either you can send a bunch of pulses as shown in the images. I can send with one sequence of PRF and the other thing with the other sequence of PRF, and I can go on repeating on a sequence of that time. Then I will be trying to find out how the differences between these two bunches or the differences happened, and I am going to try to reconstruct. So that way, when I'm using two different PRFs, the formula gets changed. Earlier we had V is minus lambda PRF by 4. As you know, the Chinese remainder theorem is the one which is going to play a role. If you wanted to know the LCM, what you'll be doing is you will take the multiplication factor of both the numbers and divide it by the HCF. Similar thing has been done. So PR of H into PR of flow is done and divided by the difference between the PRFs. So you've taken it. So that way, this is going to give your unambiguous velocity. But what about my unambiguous range? There is no improvement as such. I have two images. So both I am trying to overlay. Now whichever is up to the smallest coverage, whichever was a noisy thing, I'll plug it out. So that way my unambiguous range didn't improve because of a dual PRF, except for my unambiguous velocity. So now you can see there is a table. Now instead of SCX, I put some numbers. 10. You know it is going to be S-band system. I went from the one extreme of S-band to the lower extreme of a X-band. So I get 3 centimeters and 10 centimeters. Put different combinations of PRFs. As you know, this is the one set of PRF which IMD is putting 600 and 450 with a folded ratio of 4:3. And what the highest velocity I could achieve? 45 meter per second if it is a 10 centimeter radar. At the same time, as this 10 centimeter is only a reference, you may get up to 11 centimeters also. That way you get somewhere about 49 to 50 meters per second, which could be measured by using a dual PRF technique. At the same time, my unambiguous range also is up to 250 kilometers, which is very well valid taking to earth curvature. As when you go above, away and away, your beam is going to be away from your earth. The difference is going to happen. So normally 250 kilometers is a reasonable number, as your beam is going to be somewhere 3 to 4 kilometers away. So almost closer to your melting layer band, we can restrict up to that region. So that way, that we went with this combination with the committee to determine what PRF combination is to be operated. And there are some more numbers which has been kept. I'll be touching upon this particular fancy thing which we implemented for our cyclone tracking purpose. And for the 3 centimeters radars also, we did the calculation. Now you can see earlier with the 3 centimeter radar, which you can measure only 7 meters per second, I could go up to 32 meters per second or 25 meters per second with a staggered ratio of 4:1. Now the staggered ratio is nothing but this ratio between these two. Normally a difference of 1 is kept. Why? The subtractive part which you kept it below, it should be a prime number. Otherwise you enter into multiple locations where you may be getting a overlap and the velocity deciphering may not be feasible. So now this is one technique. As we found, unambiguous range could not be improved. So what we are trying to do is, now that phase coding which I told, so I am trying to code each bunch of pulses with a different code. So ultimately now whatever you are getting, a true spectrum will be having both of this. This phase can be represented in a frequency. That's why we have put in the spectrum domain, where if you cohere with one, I cohered with this, then when you cohere with this, all rest of the thing is going to be nice. Only the noise floor is going to go higher. It's not spoiling this. It is still about to the noise floor. So you can detect the return. Similar way, I cohere with this. Now everything becomes nice. I get this. So that way, for a second trip recovery, I'll do it with 2. If I go for a multi-trip recovery, I'll be going with 2 or 3. The phase coding can be either random, and Sachidananda and Jrenik, they proposed during 99 the SZ phase coding, which is very popular, and most of the IMD radar has this coding method. So that way, second trip means how much unambiguous range I got it, double of that I am going to get. So 500 kilometers, more than sufficient. So that way, we are using this also operationally in IMD. So I am showing some examples where you can see there is a folding happening over here. Now folding, how you can identify? This is a zero isotope. The velocity, when I discussed in radial velocity, you have to be more careful. The radar detected velocity is radial velocity. So here there is a cos factor. Cos factor came in because whatever you are trying to measure is towards or away from you. Whichever is in the perpendicular direction, there is no relative change in the phase which you can find out. So ultimately your velocity is normally going to be 0. So now here you can see the wind at the lower location comes from this direction. So I have the zero isotope here. So when I go higher and higher, this changes. As this is a PPA presentation which will be discussed on the next discussion. So this is a velocity plot, the one of the parameter which we discussed so far. You can see this blue is incoming color. All of a sudden, without going into from blue to red, it should go on this cadre, right? So I should cross white, but without crossing, when it crossed over, I say there is a folding. But of course, here from red to this, it came back. So here I am finding this is going to be the actual line. The blue is okay, this red is okay, this is a folded thing, this is a folded thing. So that's how this unfolding can be done by using a dual PRF. Where you can see here, we operated with 2 PRF, we could unfold it and we could increase the observational range. So this is one method. And second thing, certain times, whenever there is a system, the velocity goes much more higher, and the images which comes to the public domain may have a folding. In that case, there are processes which you can do. As finally, if you see, it is going to be like a sine wave like this. When you make a circle, as what you assume, there is a uniform flow. So one time you get a maximum incoming, I get a maximum outgoing, and 2 directions I get 0. So when you make a plot, here I get a maximum, then it is going to be minimal here, then again a maximum in the rear, and one more minimal, I'll get a sinusoidal wave. When this breaks over, that also indicates it's having. So that way now machine learning and other algorithms also are applied. This is a recent paper in 2023 which has come where they used the MI technique to unfold it. So it unfolded, it regenerated. And the other thing is, normally what we do is, you have to see where there is going to be a range folded thing, note the value. Now I have a scale. Now the scale, the folding you can imagine as if my scale changed away from the scale. So now what happened? This is the actual scale. I am trying to measure on the blue side here, as this is a rotational vortex, blue incoming cool colors, red outgoing. So here there is a Rankine waters or a cyclone over there. Here I measured it, I got a plus value where it should be negative. It indicates that I crossed the scale and entered into that. What number I got it? 22.74. So it is right over here. So I have to get this much value of that. So this is the unambiguous velocity 32.87 plus this total. The velocity at this point is 43 meters per second. So this way also uncoding can be done physically also, which normally we do it on the operational time. And not only that, we do different scans. especially now, as we said, only up to 250 you can see. But having a negative dip, which I can see below by using my radar, we can do a different technique of having a different elevation angles. You try to make it, and depending upon the zone, this you can see, this is for the Nivar cyclone and this is for Varda cyclone, what we did it, and we can do lot of analysis by finding velocity even beyond 250 kilometers. Though we are not putting in the public domain, as whatever you are presuming requires much of a meteorological understanding to downscale it and bring it to the reference. As you know, 60 kilometers away, your beam is 1 kilometer right. Then when you go at 400 kilometers, you are somewhere up to 8 to 10 kilometers far, and you assume there is a normal beam propagation happening. Sometimes it may not be true. So taking into all those accounts, we meteorologists use it internally like this scans we do it. We try to decipher. And this is one-time achievement which I got it. You can see this is a cyclone, but the velocity is almost very closer to zero. Why? Cyclone was exactly over the head of my radar where I am sitting right now. All the wind is rotating around. It is perpendicular to my beam at any time. I get the velocity sensed at zero wind. That's how radial wind. You should be very careful whenever you are using a Doppler derived velocity. It is a radial wind. Radial wind means only on your radial direction, whatever there is a relative motion you can find, but not on the other directions. You imagine that superficial scenario. It's almost like you entered and sat into the cyclone, heavy wind whirling around. Your radar was sensing as if there is no wind. So this is one of the lacuna which cannot be corrected to the radar. You have to rely upon other techniques. So saying with this, I conclude my first topic of discussion. Shall I proceed further? As time also we are just marching ahead, I thought I'll rush up very fast. Then we'll take up the questions. I could find some hands raising up. So I'll be completing this fast. So next we are going for different wavelength bands. As this already Pradhan sir covered, I thought I'll be doing up very fast. You know, electromagnetic wave starts right from your radio waves. Finally, it ends up to X-rays and cosmic rays. So what we are going to use? Only the microwave spectrum. We are trying to use it for radar applications. Why only microwaves? There only you have all the polar components which will be responding to your wavelengths and giving back a return. As we are using the same microwave for cooking purposes, microwave oven sprang out product of radar. A radar person who was standing with that, he had a chocolate in his pocket, Mr. Spencer. He found it got melted. He found, okay, then means there is a heating effect of microwaves. Why can't we use it for cooking? That's how in 1960s, the microwave ovens came out of radar. So we are restricting with microwave, though we say it as radio detection and reading, we are using only microwaves for the purpose. And these are the different bands which we are trying to use it in our radar application. L band, literally as a jargon we used to say, L means long range, then S means surveillance, C, a compromise band, and X is going to be the smallest band which normally we use it in weather radars. And there are other things also. We try to use carbon radar systems for some of the applications, like micro rain radars, your cloud radars. Cloud radars are normally going to be in Ka-band, and Ku-band radar is going to be your microwave radars. And when you are using a cloud radar, I require dual wavelength. As we are trying to use dual frequencies, normally we use a still more smaller frequency to amount for my antenna dimension. I go for a W band combination. So Ka with W band is used, or C with Ka band is used, or there are cases where they use even X band with Ka band. So they use two wavelengths. They try to find out in resolving the microstructure of an atmosphere. So each of the thing has its own advantage and this. So that way I am just glancing upon the different wavelength bands and what are the things are going to make a difference to it. You know, in IMD we use all three bands. Why? I could have stopped only with the S band like the developed countries which they have it. In US, the entire radar network is of S band. And what we are going with, when you are going for a C band radar systems, they used for terminal Doppler weather radars where the angular width is less and they wanted to see for a smaller range. So heterogeneity gives you more of information. As we also go with a similar environment, the environment doesn't change, but based on our perception, like you are a Goliath, then you just you go into it, and if you are a Lilliput, you get much of the thing sensible, you will not be in a position to respond to the atmospheric effects to it. So that way I compare two radars. One is the one, this is the S-band, which we were literally there. And this is the X-band radar system, which also we have it in Chennai. You can see how the variations is going to be. As to your radar equation, the backscatter return from a X-band radar is going to be much higher because of lambda power 4 dependencies. It is going to be on the lower power as we assume Rayleigh scattering. So X-band you should get more. Yes, we could get it. But what the unfortunate part? X-band suffers from attenuation. Once you say the attenuation is that my signal cannot go long. It goes weaker, weaker, weaker with time. And ultimately you can see up to this, the enhancement is there. So up to this region, all this, it has shown as weaker clouds. So whenever you try to use X-band system, especially for metropolitan applications, we go for multiple X-band radar systems, make a overlapping. From attenuation also, you can calculate how much rain is going to be derived with. So that way, IMD has a holistic view. We go with all different bands, depending upon the applications. Especially in hilly terrain, you cannot see long. Then why to put a C-band or S-band? We go for a small X-band systems. When you come for the plain, you put a larger system. If it is going to be highly cyclone prone or a thunderstorms, you go up with the S-band system. So these were the things which we kept it. There you can see we kept this also. The attenuation, how much it is going to vary. So that way your attenuation is going to increase, though my backscattering cross section improves by reducing the band. This makes a large dent to it. That's how you are getting those variations when you're going up with. So here you can see the top one is from a carbon radar. You can see even the small cirrus shootouts. But in a C-band system, this is missing. This is taken from GPM mission, which they used it. So ultimately they could find, yes, these regions, because of the sensitivity lagging, you cannot find. Only rain-bearing systems, a C-band system can be determined. So now the same thing I tried to compare with our systems. This is a X-band system. This is a S-band system. Of course, uncalibrated. This we were doing during a factory acceptance test, where you can find the X-band had a good return, but S-band had a better sensitivity. All these small echoes were visible. Could you judge anything? It is technology advancement. So-called solid-state power amplifiers, you used a big pulse. Then at the closest range, I used a weaker small pulse to sample to get some returns. So ultimately it lost all this. So that way, the technology also matters. When you are trying to use the radar, first you should try to understand the radar. That's how Sama has arranged for this course for the researchers in getting a wide view. When you are trying to use the data, you have to think about all the complexities, right from technology, application, and on the data aspects. So now this is the thing which already I covered. You can see the attenuation increases. Not only this is your normal atmospheric attenuation, it has that. And these are the frequencies. When you see the frequency goes higher and higher, or my wavelength becomes smaller and smaller, my atmospheric attenuation increases. At the same time, for a specified rain band, again you can see the attenuation goes on increasing with frequency. Especially for W band, you can see 31 dB, almost entire energy absorbed with. That's why it goes into saturation. When you are trying to use a cloud radar, it goes into saturation when there is a rain. Only clouds you can sense to it. Similarly, the scattering mechanism also goes up with, we normally assume we are in the Rayleigh scattering zone. Sometimes it goes into my region where there is going to be a fluctuation. This probably in the next lecture people will be covering, as that is one indication for hail. And sometimes you'll be getting a optical region. So this also in simulation you can find all is not going to match one or the other. The paper reference has been kept and what they used it also has been kept. If some of you are in research, you can see. And this sensitivity already we discussed. The S-band system is going to be less sensitive, and the small systems or the high frequency systems are very susceptible for the sensitivity of the atmosphere. So this is one. And cost wise, as my antenna, servo system, everything becomes larger for a bigger system. The price of the system goes up, and there is a comparative statement given here where you can use whether it is a cloud, which are the bands you can use up with. You can see S-band, I cannot use it for cloud studies, sensitivity lagging. X and C.
Sir, your mic is muted. Kannan sir. You might have touched the.
Whether it's okay now, sir?
Yeah, now it's fine.
Oh, thank you for reminding. So what you can see is when I'm using a cloud radar, you can see cloud radar is confined only to this. Even XC band also, yes, neutral. Okay, somehow it's okay. But when I go for S band, no, non-rain bearing clouds, high lag sensitivity we cannot find. At the same time, when you see for snow, yes, any bands can be used. For rain, you cannot use W band. As I told already, it is going to go for the saturation. And for heavy rain, okay, hail, you can give a color code. This also has been adapted from the recent paper which came up with. It is in AMS conference. You can see it is in the reference. So having said, now I'll go for the next topic. As the time is becoming very less, I'll just rush up in few minutes. Then I'll come for the question session. During that time, we'll go back to the slides. So now, having said all those things, you imagine like a radar, a metallic junk is there. What it does, it throws out a microwave pulse. So the pulse goes out. The pulse is going out. Whatever the pulse interacts with the target, it gives back some return. So what I get a Gaussian wave return back like this, a signal weaker than the pulse which I sent it, because it encountered all different atmospheric processes, including attenuation, scattering, reflection, what else, everything it suffered. So I got a lesser value. It came there, so I can find how much my return pulse power is going to be by sampling this. That's how PR, the received power, is going to be the integral of the entire signal centered about that particular shifted frequency from this. So I got the power. Power can be measured. Second thing, what I did, as I have a very high stable system of phase, so this is my zeroth phase. You can see there is a shift in the phase of this. So how much it shifted? It is nu which has shifted there. I had taken it, referred to the nu. Again, I did a sampling and weighted average of that. So it is the first moment on mathematical sense. On signal parlance, what I am trying to do, it is R1th lag. So I had my radar referred as R0. R1 is the one which I got it for that particular pulse return of a stipulated time. So that I am trying to cover it. I am finding velocity. So velocity, when you do it, it is going to be noisy for wiki returns. But if you have a good strengthened thing, you'll be getting a better velocity decipher. So I have the second thing which I'll get it from the radar is velocity. And the third thing is, now you can see it is a Gaussian. That means this is not the single value I got it. I got it spreaded slightly. Why? Atmosphere is not very stable. It changes with time. So first pulse interaction, I got some value. Second pulse interaction, I got some other value. So how much was the deviation from the thing which I got from the mean value is calculated. That's how I calculated this. As it is centered from this, I have taken a square. I am not bothered about the magnitude. How much there is a shift about this for the 2 sigma has been calculated with. I get this as a normal distribution function. So this is the second moment I get the spectrum bit. So Doppler radar, a single polarized Doppler radar will give you 3 parameters. One is radar reflectivity factor or a measure of a power. And second thing, it will give you velocity, which is nothing but the change in the phase or the shift of that in the frequency. And again, it is weighted with the power to it. And third is going to be my spectrum width, which can be equated as a turbulence at that right location, right? So having said, now I am coming on the mathematical terms. This already Pradhan sir has touched you on the radar equation. It is going to depend upon your pulse width, angle, and here I have my Z. What is this? Z is the one which we say it as radar reflectivity factor, and why it is Z will be coming in the next slide. Normally it is going to be independent of all parameters, either whether it is this X band, C band, S band, it should give the same value. It is going to be directly proportional to the 6th power of the droplet. So that is, there is integration and 6th power of droplet, and there is a number distribution presumed ND. We are integrating for the entire thing. You try to get radar reflectivity factor dBz, and normal measured value in the data will be from -32 to +93. But normally what we have observed so far is it goes right up to -30, which is equivalent to 0.01 millimeter per 6 by meter cube. And the maximum sensitivity is 76.5 in a hailstorm. So these are the maximum you can find. When I convert into linear terms, you can see this is to the thickness of my air. Of course, I lost in plenty. But the other one you can see it is almost to the dimension of the earth. So I have to measure both the things with equal differences. That's how we proposed a logarithmic scale for Z in dBz. That's how power is measured in dBz, equivalence of power. But of course, I take a volume that I'll be discussing subsequently. And velocity, as I told, no, the first lag, R1. The first lag is taken, and this cos alpha came because of that 90-degree interaction, lambda PRF by 4, which already we derived. Spectrum width, we assumed that normal distribution happening. That's why 2 by 3 ln this came, and between these two lags, the second and the first lag has been taken and normalized with pi. So these three are there. I am not going to touch the rest of the parameters of dual polarization, as this is going to be discussed subsequently. Now, most of the participants who are not belonging to radar, they'll be very curious to know what is this specific unit, Z. And this is proposed by Stuart Marshall, the same person who discovered the Marshall-Palmer equation, proposed the Marshall-Palmer equation. And why he did? Simply to make the people to spell proper English. As you know, most of the US people, of course, now it has become a parlance. Even in India, we used to say Z. But he wanted to correct that. As Canadians, Germans, and most of the English-speaking people, they spell Z. Not in US, as most of the technology started developing in US. This person wanted to make it proper. This I borrowed from the paper. The paper also is given then. The invention of radar meteorology, it came in Bulletin of American Met Society, 1986. The page numbers are referred. I copied it as such. Marshall chose the symbol Z and even thought some Americans to pronounce it Z. But most unfortunate part is even nowadays we people say DBZ. It is DBZ, not DBZ. So that is there. So he spelled, this is borrowed directly from the paper. So on the radar equation, first is radar reflectivity factor, which is going to be the Rayleigh scattering effect lambda by 4, d power 6 by v. But I taken Z, taking out all these things into the radar equation. That's how it is going to be having a proportionality of d power 6. But when I am trying to measure Z, I measure like this. On the reverse scale of that, I keep Z here and all other things I push to the other direction. That's how that minor variations of this lambda, that thing comes up with, which gets compensated with the radar constant. And minor variations, because of the scattering effect, is not attributed. That will be playing a role. Attenuation factors will be playing a role. So this, except for these variations, you should not get any variation in dBz, as it is independent of your system, right? So what are the various assumptions we did this? It is kept over there. I'm skipping this. So now what are the parameters, how it looks? dBz values, it is Z, radar reflectivity factor or radar reflectivity. Then V, the radial velocity. W, the spectrum width. The three base movements, finally we know how it came on theoretical sense and on the engineering parlance and on the meteorological aspects also. Like here you can see, it is a cyclonic storm. Here the clouds are more, my back receipt powers are higher. So that has been done. You can see at the eyewall region it is there, on spiral bands it's there. And velocity, you can see it is a rotational vortex here. My radar is somewhere here. So ultimately this is the rotation in the northern plains. You get incoming and outgoing velocity. And my radar is here. Now the system came to my left. So the vortex is rotating here. Here is incoming, and this you can see the change in the direction of the colors also. Now when coming to the spectrum width, you can see there is a high turbulence only on the spiral band region, indicating the system is going to last long. When it comes closer over the land, a lot of surface frictional effects started happening. You can see the spectrum width came on the higher values. Again, it is in meter per second. Normally it is 0 to 8 meter per second is the scale we keep it. And once it again entered into SUHI, this data is from Paradeep radar. You can see once it entered back there, again the spectrum width starts reducing. So completing that, the last part is on the application, the ZR relationship. So what we covered, 4 topics: Doppler effect, how it is there, and how we use different bands, and this products we covered. Now with this, I'll slide just 2 slides. Most of the thing I'll try to skip. So what I try to do is, the basic difference in a rain gauge and radar is, rain gauge sits on the ground, 100 centimeters square. Ultimately, how much is going to be a catchment area is going to be somewhere 320 centimeters square. But in the radar, I am trying to sample a volume. At 30 kilometers, this much is the volume which I am trying to sample for 1 microsecond. That means a smaller pulse. So that much of the droplets which came into that, I got back a value. But in the ground, I kept a very small orifice open and I tried to measure how much raindrops entered in. So what I measure is Z is going to be proportional to d power 6, and rain rate is nothing but my volume of the droplet 4 by 3 pi r cube. Then my fall speed. So this will give me the rate of drop falling down. This, as we kept d cube here, 4 by 3 pi r cube, the d has brought the divided factor by 2 to it. That's why we are getting pi by 6. As 4, it has to become 8. So 2 it got absorbed, remaining it came there. So it became 6. So this is going to be, when I try to see directly, Z and R can be equated, of course, in non-linear terms. But this ratio is going to be somewhere to the power of lesser than 2. So the default Marshall-Pohlman coefficient, which was derived purely on mathematical, these observations, is Z, your radar reflectivity factor in linear terms, not on log scale, is equal to A R power B. R is your rain rate, A and B are constant. The default Marshall-Palmer constants are 200 and 1.6, which in turn is a measure of your drop size distribution. So now what are the ambiguities in it? Now, as dBz is nothing but the power received back by a sampled volume of 1 meter cube. Imagine I kept only one droplet of 3 millimeter dimension. I get 729 millimeter power 6 by meter cube as a linear scale. In dBz scale, it is 28.63. But I kept 729 droplets into it. I get the similar value. Now, both the dBz values are the same, but my realized rain rates are varied. So directly Z and R doesn't match unless you do know the drop size distribution. And where come the drop size distribution comes in? Because of this coefficients, which we presumed to be normally happening with default Palmer equation, which may not be right most of the time. So each radar we try to do a calibration. And in the same reverse way, what is shown is the rain rate can be equal, but my dBz also may vary. For a single polarized radar, that's why we went for dual polarized radar. To say to that, single polarized radar, the rain rates are having ambiguity, but it doesn't mean that it doesn't sense. So that way you will be changing A and B coefficients. Here I kept the default coefficients and how much is going to be there based to the different rain rates has been plotted. And we did exercise for different radars, how much it is going to be. We change the coefficients. Like Chennai is running at 265, 67 and 1.3. A is not 200. We made it to 267. This Dr. Suresh did later, and we found minor variations. We are doing it as to the case B on the case related analysis basis. Similar way, Shar we did it. We changed. Delhi also we changed. Calcutta also has been changed. And Dr. Raghavan sir, as Chandra sir was giving the memorial lecture on the very first day, he used to normally comment. As many number of researchers are there, that many number of this coefficients normally used to be. You can see different coefficients we applied when we had a problem. That time, the president of SAMA, he was the DGM of IMD, Ajit Tyagi sir. There was a heavy rainfall happening over there. We got our radar installed in Delhi in 2010, 9-10. So ultimately, the Palm radar was sensing very less echoes. He was saying that this should be looked in. As he had all the scientific spirit, which he is still carrying upon, we did all these variations by the coefficients, and we found which came closer to the reality, and we said Delhi radar's coefficients are to be changed. Now, whatever we are taking is this Marshall-Palmer. If you want, different coefficients also can be attempted, especially the Pareto combinations will be giving you the outliners also properly sensed. So this is a constant research which is still ongoing. And when you want to match the rain with the ground reality, it's not only the coefficient. Already we saw the distribution functions. In the radar location, what we do, we try to adjust the clutter filters. Like here you can see, this was the cross section which I made it. So this is uncorrected. The corrected thing, you can see it removed the cloud. Why? There may be interference or the signatures were not proper. We try to correct that at the radar side. So if you have a uncalibrated, uncorrected radar, this clutter filtering also will create a much difficulty in rain estimate. So this in station we do. And attenuation, you can see this is the radar side and this is a very big echo. You can see all your signals gone up. That we try to correct it back by the rain rate calculations based to the rain rate derivation. So attenuation correction we do. Partial beam blockage, we are not doing. Bright band calculation, yes, if there is a bright band, especially at the melting layer, you get a higher reflectivity. We try to correct it. So that is normally done. Few of the radars, it's not implemented. And point clutters, especially if you have ships, aircraft, that also will be showing. So that way, that also will create artifacts. Some of the images I kept, which went to the website. So this you can see rib-like fashion. We assume the intensity pertained for the next 10 minutes, but it was a fast, rapid moving cloud. We get fishbone-like structures. So this, you will be getting 144 products for one day. This is accumulation. So it presumed here only it was raining for the next 10 minutes, but the cloud literally moved here. All of a sudden I got that. So we'll be getting this rib-like patterns, and these are the ship movements. You can see sudden enhancement. This is again the ship movement in Mumbai. And this is the bright band, how it will be creating artifact. And these are the beam blockage zones where the beam blockage has filtered much of the echoes to it. And these are RF interferences. Sometimes that also creates ambiguity. Saying to that dual polarization, yes, it improves. You can see this single pole. This is dual pole. We got a good reflectivity value over that. Now the Delhi radar is operational with the dual pole rainfall rates, and most of the dual pole radars we used. But irrespective of that, as in dual pole, we go again with the residual algorithm with 3 different scales. At smaller rain rates, only ZDR can be trusted, your KDP becomes noisy. But in the medium and higher rain rates, your KDP and ZDR can be used. So that way we classify, we used it in getting the earlier product. So you got this rain better improved. But of course, whether that is the tail. So when we did that, some case studies we did, like here, this is a dust storm at Delhi. No much rain realized, but the radar was showing such a higher rainfall. So these like artifacts because of the atmosphere do prevail, as radar is going to be a remote sensing device. Saying all those things, then can we say radar is not good in precipitation? No, you cannot say. Each are unique observables. Like I sampled a volume, the rain gauge measured a small point. Here you can see these are the rain gauge locations. And the rain, you can see, it eluded most of the rain gauges. Here the rain was more. So ultimately, you presume this was the actual value, the ground measurements, you predicted that was the rainfall happened to that region, but there could be a very closer region because of the high variability of the rainfall. You may be getting a very excessive rain at different locations. So yes, spatial rain, if it is to be calculated, there is no substitute for radar at present, irrespective of all the anomalies which we said. You have to do a ground validation, as finally you have to compare with your ground truth. We use a lot of techniques in doing it, and we try to do. So that way radar has a better spatial and temporal coverage. Even radar data is used for the hydro estimator correction in INSAT 3D and 3DR. We are sending the data in real time. That way radar has its own weightage. And single polarized radar, of course, we have still 16 IMD, which goes for the upgradation at a shorter time. We have to live with that small anomalies coming from that. With that, I'll conclude my discussions. Now I am open for questions.
Yeah, so
Thank you. Thank you very much. Right.
So Dr. Ravilas, can I go for that questions answer?
Just 1 minute. We have a photo session.
Photo session.
Yeah. And Kannan sir, it was a very power-packed presentation.
Yes,
It's
yes.
a lot of energy. so it's a very nice watching with enthusiasm. So may I request all panelists to switch on their camera.
My camera will not work today, so I'm fine with this status.
So you can stop sharing the screen.
Yes, sir.
Yes.
Mohan, please.
Yes, everyone be ready. Okay, 3, 2, 1. Click. Thank you, sir.
Thank you. Now I request Swagata to handle the QA session.
Thanks a lot, sir. And as you mentioned that it was a power-packed presentation, it's true. There are already few questions when he was giving the lecture. So from there, I am starting the questions. The first, what is the difference between Radar and SODAR, the
Ah.
simplest way.
Radar uses radio waves or microwaves to be more proper in finding the range. However, SODAR uses sound for propagation and finding the range. It has its own application. SODAR for deep sea missions and other things, we normally go for SODAR, as microwave cannot percolate much deep into. So you have to go with only sound for sampling the range at the locations where your electromagnetic signals cannot propagate. That's how SODAR has its own application in range finding. Similar way, radar also has its own thing. And second thing is, shall I go with the question, sir, and proceed with that? There is another question. What are the difference bands in the radar? I shown.
Yeah. You can see the questions and can go. Yeah.
So the different bands, what we try to say is, in meteorological term, those bands has been kept. It is offspring from defense. So we kept that S, C, X, Ka, Ku, different bands are there. And it is attributed to my operational wavelength or the frequency. Based to the frequency, as I shown, there is going to be a variation in sensitivity, or it is going to have an implication on your atmospheric parameter, which is to be studied. If a cloud is to be studied, I'll go for a Ka band or a K band or a V, W band, I'm going to be there. If I am going to use it for cyclone purpose, I go for a S band. Based to the application, if I cannot put a S band radar, then I go for a compromise band of a C band. And for minor clouds, you can use X band. So that is the one. So that is what they say, different bands in the radar meteorology, which normally is used. Of course, the other bands, UHF, P bands also were used earlier. Nowadays, it is not that common. And there is one more question. What is the factors? Doppler dilemma is not clear, please. So what Doppler dilemma is, as already we discussed, the product of my unambiguous range because of my operational PRF is going to either permit me to go for seeing the velocity better at the cost of my range restriction. So I cannot see very far and I cannot see a very larger velocity. So that's what is going to be there. So if I want to see the velocity, then I lose my range. It gets lesser because of the PRF, and there are methods to correct it. We saw some 2-3 methods, the dual PRF and other things.
A big boy's a young chief, and they... Let's go.
And finally, I'll go to the next thing. What are the factors affecting range accuracy of the radar? The range accuracy is affected. If you see on the engineering parlance, it's my rise time and falls time also creates a small ambiguity in the range. If you are going for a phase coded radar, if I'm using a linear frequency modulation coding, it is going to create range side loops. There also, I'll be having a problem in my range detection. Otherwise, if you have a very stable system, your range is more accurate, going to be C tau by 2. If I use 150, if I use 1 microsecond, my range accuracy is somewhere up to 150 meters. So whatever is between 150 meters, I can sample it. And nowadays, when we go with the phase coded radars, we can go up to 50 meters or 25 meters. So that way codings has come. So that way the range accuracy is going to be in the order of few meters. Then what are these numbers indicated under PRF? So these are the common PRFs which I shown in this slide, 300, 400, just for example I taken. The maximum limit was shown on the first slide. The slides have been given to SAMA organizers. They'll be giving you the slide to you. It will be sent. You can start using it. And you can respond back to my mail also if I could not answer all the questions here. So PRF L is nothing but lower PRF, PRF H is the higher PRF. So that was the thing which I used the nomenclature in my slides. How many types of radar need to be installed to cover the old weather scenario? Old weather scenario, now if you go for phased array radar, tornadoes and dust devils can be done. Otherwise, these even at the present parlance, you cannot sense. Whatever you can sense is only on the meso scale. Tornado sensing also, once it is close to the radar only you can do. So somewhere the weather events spanning slightly away from your kilometer range, going up to the coverage of 250 kilometers can be sensed in your radar. Can you elaborate on calibration of radar? Calibration of radar, IMD is going to organize a session quite soon, as this is going to have an audience of all the people around. I am skipping this question. There are variations you can do. Power calibration we try to do. Phase calibration also we try to do. And each parameter, how much losses are there, we correct it, we try to do it. But this entire procedure, we'll be organizing a separate session for spanning of a more period, that we'll be sharing the details to Sama. Sama also can pass it upon to the participants who came here. We'll be having that as a separate session, which we had the previous year also. In Machilipatnam we did, this time we are planning in Chennai. That will be announced quite soon. So I am skipping this question, only partial answer is given. What is the minimum radar range near the radar station? Now minimum range again is dictated by my pulse width, but if you go on true engineering parlance, my far field, till my far field, whatever I am going to get, cannot be used as a proper return. Normally when I use an X-band system, then you can assume that the initial 600 to 700 meters is going to be unusable data. Though you get some returns, if I use 15 meters as sampling, I will get it, but those data are not fully reliable. Thank you. Thank you. Our SRI is more accurate than rain product. SRI is nothing but surface rainfall intensity. From DBZ, I am trying to calculate the rain rate from remote sensing devices. We shown there are lot many artifacts. Yes, presentation you will be getting it. Some I will be sending it to you. Already I shared to them in the PDF form, which will be given to you, except for the Doppler, which also I borrowed from the web. Nothing is animated. You can start using it. Give credits to Sama and IMD for that when the devices are going to be used there. Is there any advantage for using domes? What is that? RAM ones. I am not sure what this trying is. I am not sure what is the RAM ones. The question which has been asked at 4:30, I am not sure. Can we use radar on a mountain if the med station is on the islands? Yes, in Himalayas we are using. Only unfortunate part is what we are going to sample is almost to that level. Into the valley, which is somewhere in Himalayas and all, we go to up to 3 kilometers height. What is going to be realized below? Anyway, the cloud has to follow on the top. It will be falling down. So that way you can use it, but it is to be calibrated with the ground. If you are not doing a proper calibration or ground correlation, there is going to be variation. Is there a thumb rule that provides a particular reflectivity corresponds to particular range of precipitation? Yes, that thumb rule only is the default Marshall-Balmer equation or the residual algorithm, but it is subjective as it is a remote sensing device. Can we track stealth with EWR? Yes. Some of the non-precipitation echoes which we could track, especially when there was a defense operation, we could find that in Delhi radar, we found much of the time that they used to disguise, they sprayed. So that signatures we felt. Even in Chennai radar, whenever there is a launch or some Navy activities, we get the phase shift in our radar. We try to measure it, it can be done. But unless the person is good in radar technology, he will not be knowing whether it is a return from cloud or something else. Partially it is yes, but you cannot track an aircraft or something to it. It's only that you can infer something is happening, but the exact location cannot be pinpointed. What about radar observers? Yes, there are a lot many things which will absorb microwaves, especially the stealth aircrafts. There is a problem on that. If you have that in plenty, your radar cannot sense. But of course, our targets are going to be weather and weather related, which doesn't disguise, normally happens in the nature. You can find out unless there is a clutter in between. Comparison between rain gauge and radar for making validation. I shown some 3 or 4 case studies in my presentation. The variations out of wind and other thing has been highlighted. I shown only the deviation. Doesn't mean that it is going to be always deviated. Most of the times it matches. When radar operation, why 2 PRF is used? I told dual PRF will be helping you. If I use 450 only, 2 elevation data, collect some of our radars. No, in IMD radars, we try to use dual PRF for the volumetric scan, and we go for a single PRF for a long range surveillance, especially 250 PRF or 300 PRF we use up to getting 500 kilometers. Can you email the attendance link? This Sama will be giving. If reflected data is unturned, then how it is compensated? No way. Unless I get a back return, I will not have any provision to correct or improve because of nation and other thing. That's why we told for a X and W band, you cannot do precipitation studies. How can we detect sea breeze from a gust front using? Yeah, this is a good question. Sea breeze front can be detected in radar, but not fog. Why? Fog, the particle sizes are so smaller. D power 6 is going to be that much later. It goes into the noise. Radar normally cannot detect fog. The weather radars which presently used in IMD. But sea breeze, But the sea breeze, what it does is, it is a refractive index in homogeneity, almost like your Bragg scattering, which is happening there. I get a very large lead surface. You will be getting sea breeze. Yes, we do track sea breezes. And certain times when there is a very strong summer, we used to go for the nowcasting of sea breeze also, especially during launch related activities. This was one of the key parameters which our rocket launchers used to ask, whether there is a sea breeze, whether there is a refractive index anomaly, what are the things you can infer from your radar. We used to reverse calculate and give the feedbacks to them. Which direction the thunderstorm is going, already we shown. Only from reflectivity means with the animation only you can find. But using velocity, there only the Doppler radar comes in. You will be knowing which direction it's going to move. Are we seeing quality control radar products in IMD website? Yes. I told most of the things are quality control except for some. The B blockage corrections and the thing is not done. As such, we are presenting. That way, you'll be getting that blockages. RF interferences, to the maximum, we try to quality control. Some of the things, the strange interferences which happen every now and then, it comes up with. CUSAT also helped us in doing a survey, RF survey. Before putting the radar itself, we take a precaution. What are the things we have to go up with? So that way, quality control, right from the radar side starting, it goes up with. Why many papers use radar only reflectivity? Why parameters, especially the spectral width? Spectral width, normally why it is not used is, I am trying to measure the turbulence or the variation in the velocity between the pulses. My antenna also is moving. You imagine I moved my antenna faster, which the person will not know. Then when he is trying to use the product, he may infer my target. It will be reflected on the target, right? As if it got some turbulence over there. That's how spectral width product, and is not putting the website, but this product is being given to all our aviation operators to find out the shear happening closer to the touchdown zone. So I think with that I am completing most of the questions. Thank you everyone for the patience and some of for giving the opportunity. I'm very grateful for this, and the activities which you have taken is going to be highly beneficial for IMD. As we are spanning with a very large radar network, people who are attending this, they'll be doing a lot of research and the country itself will be finding a good scientific growth. Thank you all.
Thanks a lot, sir. Your presentation was power-packed. Dr. Ovela said, mentioned that time. I think your question answer session is, we need more superlative degree for that.
More powerful.
Sir, over to you.
Yeah, thank you, Kannan sir, for a enlightening and engaging presentation where you have shown your scholarly approach and philosophical and scholarly approach in delivering the lecture. Thank you very much. Before moving to the formal vote of thanks, I request Tyagi sir to have some comments.
Kannan, thank you so much for really engrossing and very, very engaging and very insightful presentation. I'm sure participants have benefited and they will make use of your offer to get in touch if you want to follow up. You have shared your PPT, so that is also going to be a great help. Its recording also will be available to the participants, and even after that, if they have got some more clarification required, your offer to get in touch with them is most welcome. And as you have said that this is a platform to create more human resources in this field, which is useful for IMD country. So that is what the SAMA is doing. Thank you.
Now I request Somesh sir to have few words.
Thank you very much, Dr. Vilas. So how deep is the mud? It depends upon whom you are asking. A very nice slide that you showed, Dr. Kannan. I see a lot of changes in you in the last 10 years. I saw you for the first time. And I would like to also, I see that still more than 100 participants are there present. That shows that how good and how interesting your lecture was. The participants, I know some of the participants might be scared of the equations that you showed to them, but I would suggest the participant that don't get scared with those equations. They're not very hard. If you just look at the equations carefully, you will just understand that they are just nothing but the formulae for different parameters of the radars. And of course, besides this lecture which is delivered here, if you really want to learn about the Doppler radar, weather radar, you should read the textbook. Some of the textbook, I think one of the textbook was suggested by Professor Chandrasekhar on the very first day. But we can suggest some more textbooks. Dr. Kannan can suggest, or Dr. Devendra Pradhan is not here, but we can certainly suggest you some basic textbooks on radar meteorology that you should go through if you really want to learn the subject. And I'm sure that, I mean, out of those 1,175 participants who have registered for this course since yesterday, I know that their backgrounds are so different, but I mean, if some of them, they just wanted to probably attend for curiosity. Some of them probably wanted to attend just to get a certificate, participation certificate, or maybe a grade certificate if they're a little bit more serious. But those who really want to learn the subject, and especially those who are from the operational organizations in different countries, until last week, more than 46 countries, people had registered for this course. I guess it must have increased. The number of countries must have increased by today. But all those people who have registered from different countries, if you are from the operational side, just trying to use the radar images for weather forecasting, day-to-day weather forecasting, of course, it is very, very important for you because Dr. Kannan is right in the field of weather forecasting, interpretation of the Doppler weather radar products, and not only a good scientist, but also I see that he has become a refined speaker, I mean, a professor type of person who is involved in the subject while teaching. So you would definitely greatly benefit. I'm sure that from his lecture you must have benefited. And even if you have not understood much, please go through the video on the YouTube again and again, maybe twice, thrice, 5 times, 10 times. And I'm sure by going through that many times, it will be clear to you completely. So please do that, and we wish you all the best. Thank you once again, Dr. Kannan, for a very interesting talk and very, very compact subject, putting everything in a very, very compact way. So thank you so much.
Thank you, sir. Feel blessed.
Now it is time for formal vote of thanks. I request Dr. Mohan Kumar Das to propose the vote of thanks.
Thank you very much, Dr. Abhilash. Honored guest, esteemed speakers, valued colleagues, and dear participants. As we bring this insightful and enriching session to a close, it is my great privilege to offer a vote of thanks on behalf of the South Asian Meteorological Association, SAMA, and the Advanced Center for Atmospheric Radar Research, ACARR, and the Cochin University of Science and Technology, CUSAT, India. First and foremost, I would like to extend our deepest appreciation to Professor Dr. Someshwar Das, sir, Secretary of SAMA, for his warm welcome address that perfectly set the tone of today's event. Your steadfast commitment to our association is truly admirable. A heartfelt thank you goes to Air Vice Marshal Retired Professor Dr. Ojit Tyagi, sir, President of SAMA, for your inspiring opening. Your vision and leadership continue to guide and elevate SAMA to new heights. Our gratitude extends to Dr. Srikala PP from CUSAT for introducing the speaker. Your commitment to advancing meteorological research is greatly valued. A special thanks to Dr. B. Orul Mala Kannan, Scientist F at the Indian Meteorological Department and Chairman of your expertise on the Doppler effect in electromagnetic waves, particularly regarding the unambiguous range and velocity, Doppler Dilemma, and Doppler Weather Radar across different bands, has significantly deepened our understanding. Additionally, your valued insights into the basic zeta relationship and the base products from single polarization Doppler weather radars, ZVW, are immensely appreciated. We deeply appreciate Dr. Swagata Paira for moderating the Q&A session. Your efforts ensured a lively and productive discussion. A big thank you to Dr. Avilash Shukumara Pillai, Director of ACARR and Program Convener, for overseeing the entire session. Your organizational skill and dedication are crucial to the event success. Lastly, I'd like to thank you all the participants for their active engagement and contributions. Your presence and enthusiasm make these events truly worthwhile. Once again, thank you all for making this session a grand success. We look forward to your continued support and participation in future events. With sincere gratitude and warm wishes for a wonderful day ahead. Thank you.
Thank you also to Dr. Mohan, Joint Secretary of SAMA from Bangladesh and Executive Director of the NOAMI. Thank you.
Thank you. Thank you very much, sir. Next lecture in this series will be on 22nd June, on next Saturday, by Dr. Gajendra Kumar from India Meteorological Department. See you then. Bye-bye. Thank you.
Bye.